Hey everyone, I'm Olivier Mpari Batenda, a qualified mechanical engineer, and I'm absolutely thrilled to welcome all of you secondary technical students to this explainer. Today, we're unlocking the secrets of the modern workshop, and we're going to explore the incredibly exciting world of CNC machining. You know, if you've ever wondered how engineers take a wild idea from a simple sketch and turn it into a perfectly precise physical piece of metal, well, you're in exactly the right place. In this explainer, we're going to follow the life of a single concrete object, a custom metal bracket. We'll trace its journey all the way from just a digital dream on a computer screen to a physical reality that you can actually hold in your hands. So, here's our roadmap for today's journey. First, the magic of CNC. Second, designing the part. Third, the machine's language. Fourth, setting up the cut. Fifth, machining the part. And finally, number 6, your future in engineering. Section 1. The magic of CNC. What exactly is it? Okay, let's dive right into this. Back in the old days of manufacturing, making something like a metal bracket meant a machinist had to stand at a manual mill, literally turning hand wheels to carve away the metal. It took immense skill, but man, it was slow, and making 100 identical brackets, incredibly tough. Enter the CNC machine. CNC actually stands for Computer Numerical Control. Instead of turning wheels by hand, we let a computer drive the cutting tools using pre-programmed software. This automates the whole shebang, whether we're cutting metal, plastic, or wood. And the real magic here? It gives us perfect, repeatable, high precision every single time. So if we need just one custom metal bracket, or 10,000 of them, the CNC machine delivers identical results flawlessly.
Section 2. Designing the part, the CAD and CAM journey.
Every great physical part, including our custom metal bracket, starts its life as a digital idea. Let's look at how we build this bracket step by step. Step 1, CAD design. Step 2, CAM translation. Step 3, G-code generation. And finally, Step 4, physical machining. It's a beautiful, logical flow from mind to matter. To really understand steps 1 and 2, we need to look at CAD and CAM. Think of CAD, or computer-aided design, as your digital drafting table. This is the software we use to actually design our metal bracket in 2D or 3D. We define its shape, its holes, its exact dimensions. It's essentially the blueprint. But here's the catch. A CNC machine can't read a CAD drawing directly. That is where CAM comes in. CAM stands for Computer-Aided Manufacturing, and it acts as our translator. It takes that beautiful 3D blueprint from CAD and figures out exactly how a physical tool needs to move to create it, converting those digital shapes into specific CNC instructions. Section 3. The machine's language, speaking in codes. Because machines, as unbelievably smart as they are, don't speak English or Kinyarwanda, they speak in highly specific codes. Once our CAM software finishes translating, it outputs what we call a part program. The part program is the master script our machine will follow to carve out our bracket. It contains all the coded instructions guiding the CNC machine on operations like cutting and drilling. It tells the machine exactly which tool path to take, what tool to select, and how fast everything should spin. It's quite literally the brain of our operation for this specific job. Now, what's really fascinating is how we break down that part program into 2 distinct dialects, G-code and M-code. Think of G-code as the steering wheel and the gas pedal driving the tool. It controls the geometrical movements, telling the machine to position the tool at a specific coordinate, how fast to feed the cutter into the metal, and exactly how deep to cut. On the other hand, M-code acts more like the switches on your dashboard. It controls non-geometrical or machine functions. M-codes are what turn the spinning spindle on or off, tell the machine to change the tool, or spray coolant to keep the metal from overheating. Working together, G and M codes conduct the entire mechanical symphony. Section 4. Setting up the cut. Preparing the machine. All right, so we've got our digital design and our coded instructions. But before the machine starts aggressively cutting into the metal, we have to lock everything down safely in the physical world. The absolutely crucial part of this physical setup is the fixture. You could have the best code in the world, but if your block of raw metal vibrates or shifts even a fraction of a millimeter while being cut, your bracket is ruined. The fixture is a heavy-duty clamping device, essentially a giant seatbelt for our metal bracket. It grabs onto our raw material, our workpiece, and holds it absolutely securely during machining. This guarantees the stability and precision required for the CNC machine to do its flawless work. As we set up the machine, we also have to think about its physical capabilities, specifically its axes, 3, 4, or 5. These numbers represent the directional movements of the machine. A standard 3-axis machine can move left and right on the x-axis, forward and back on the y-axis, and up and down on the z-axis. But as a mechanical engineer, I can tell you that when you step up to 4 or 5 axes, the machine can actually tilt and rotate the workpiece or the tool head. This allows us engineers to cut incredibly complex shapes, reaching under and around the part without ever having to unclamp it from the fixture. It looks like robotic magic, but I promise you it's pure, precise engineering.
Section 5. Machining the part, the cutting process.
Okay, we're securely fixtured, our code is loaded, and the machine is homed. The metal chips are about to fly. So the critical point here is how we manage what are called the cutting parameters: cutting speed, feed rate, depth of cut, and spindle speed. These 4 variables are the secret recipe for a successful part. As technical students, you'll quickly learn that machining isn't just about forcing a tool through metal, it's about balance. If you feed the tool too fast, it snaps. If you spin the spindle too slow, you get a terrible, rough finish on your bracket. Balancing these parameters is how we ensure both machining efficiency, so the job gets done quickly, and top-tier high quality for our final physical bracket.
Now, as you watch the machine work, you'll notice something really striking. The tool will slowly and deliberately carve a hole, and then, suddenly, whoosh, it zips incredibly fast across the workpiece to start the next hole. This is called rapid traverse. It's the fast movement of the tool or work table between operations, moving through midair without actually cutting anything. Why does this matter? Because in a busy machine shop, time is money. By moving between cuts as fast as physically possible, rapid traverse saves crucial manufacturing time.
While all of this cutting and rapid traversing is happening, the operator is constantly monitoring the DRO, or digital readout. Picture a glowing screen of numbers right next to the machine. These numbers show the exact real-time physical position of the machine's components, like the spindle or the tool. The DRO is there to enhance precision. It guides the operator's eye, proving in real time that the physical tool is standing at the exact coordinates the part program dictated. It bridges that final gap between the digital instructions and the physical reality of our bracket.
Section 6. Your future in engineering, the next generation.
And just like that, our metal bracket is finished, perfectly smooth and dimensionally accurate. This brings us to the most important part of this explainer. You've seen how we start with a simple thought, draft it in CAD, translate it through CAM into G-code, secure the raw material in a fixture, and let the CNC machine perfectly carve out our metal bracket. As secondary technical students, you are looking at the exact tools that build our modern world. I mean, from airplane wings to medical devices to the very phones in your pockets, it all relies on this technology. So my question to you is this. Now that you understand how CNC turns a digital dream into a physical reality, what will you choose to design and build? The tools are here, the machine language is waiting to be learned, and the future is absolutely yours to shape. Go out there and start creating. Thank you so much for joining me on this explainer.